Yeah, nice to meet you all. And I'll be taking your System Verilog Basics course. And the intent of this course is covering all the basic topics of System Verilog. And going forward, if needed, and as per the requirements, we may add the advanced topics as well. So before we start, can I get a brief intro about you guys, like the background and all that? Anyone can start. Hello. Anybody speaking?
Yes, sir. Hello.
Yeah.
Sir, like I am in MTech and at IIIT Allahabad in microelectronics only. And
okay.
I had some doubts like about verification profile. Can I ask?
We can we cover that at the end of the meeting?
Okay. Yes, sir.
Yeah.
Yes, sir.
So, like all of you are from different colleges, or you belong to same colleges?
60% of them from like MTech and 40% from the BTech. All are from different colleges only.
Okay. Good to know. And I expect that you guys have some exposure to the hardware description language, maybe Verilog or VSTL during your course in BTech or MTech. So my entire System Verilog course will be based on that assumption that you have been exposed to some basics of digital design and hardware description languages. So yeah. Okay, I'll move forward. So that's the basic I wanted to know the background and my assumptions. I hope that is clear to you. So before I start, we can, like, if you feel like there's any doubt with you with respect to the course or any topic, you can ask right away. You don't have to wait for the end of the meeting. Other than the topics like just someone asked, so those topics we can cover at the end of the meeting. Okay, so let me start. So this is the brief course outline that we'll be covering in this course, and we'll start with the introduction of System Verilog, and we'll cover the data types, the parameters, packages, interface, and mode ports. So most of them you may have heard in VSTL or Verilog also, but there are other concepts which probably you didn't cover in Verilog or VSTL, which are very useful, especially for the verification aspects, like the procedural blocks and procedural statements and control for task and function, concurrency, event regions, program block. And we'll do 1 or 2 lab assignments covering all these topics. Okay. So to start with, why do we need System Verilog? Like, what was the limitations of Verilog or VSTL for that matter? So,
sir,
like, why
sorry to interrupt. Are you sharing your screen, sir? It is in the first slide only. System Verilog basics.
I have moved to introduction. Are you not able to see this?
Yeah, guys, is it the same for you all or?
No. It is introduction.
No, you can see the introduction slide.
It's changing. Working.
Okay, sir. I will rejoin.
Maybe you can. Maybe. Yeah, maybe you can rejoin. Yeah.
Okay, thank you.
Let me bring the chat here. Yeah. You can ping if there's any question. I'll look at the chat window and reply to you. So what I was saying is, why do we need another language, System Verilog? Because there are already so many languages like Verilog or VSTL, and those are probably really good for a design perspective. But then why do we need System Verilog? So if you look at Verilog and VSTL, these are hardware description languages. So basically, you can define your hardware pretty well using those languages, the FSMs or the combinational logics. But what about the verification? So verification was not so complex earlier because the complexity of the design was low, and the test cases required to test that design didn't require so many scenarios or so many stimulus. We call this stimulus in our from the System Verilog or the UVM perspective. The stimulus is basically what we give input to the design to verify a certain use case. So since the design was not complex. We didn't require as complex test bench, and it was easy to code those low complex test bench into Verilog or VSDL. But with the increased complexity in the design, it's no longer feasible to code each and every test, and it's no longer scalable or reusable across projects. And with the time to market, and so you may have heard in semiconductor is all about time to market. If you see, compare AMD and Intel, so whoever comes first in the market wins a lot of market share. So it's all about time to market. So and there are other factors like PPA, performance, power, and area though, but even time to market is very important. So you need something scalable and reusable, so that because you cannot code entire test bench new for every test, every project. And with the complexity and like even is medium complex IP will require like more than 10 or 50 of engineers, verification engineers, to code a test bench which is not built from scratch. So imagine if you build every test bench from scratch, you'll need like hundreds of engineers working for a year to build a test bench. So that's how the complexity of the test bench has grown. So you need a concept like a randomized stimulus generation. So let's consider an adder, a 2-bit adder. Okay, so there are 2 bits input signals, A and B. So the total combinations are 4, 0, 0, 0, 1, 1, 0, and 1, 1. But if let's say there's a GPU, consider GPU, you can't even imagine how many combinations will be there. So it's not possible to test every combinations of a complex IP. For adder 4 combinations, you can test them right away, but not possible for a complex IP like a DDR or a processor or a GPU. So there we use the concept of randomized stimulus generation, where we randomly generate the scenarios. Okay, like there may be billions of scenarios. We randomly generate one of them, and we verify like around maybe 1 or 2 million scenarios, and we say okay, the verification is done. But we do not choose them intentionally that we'll verify this particular scenarios. It's random. So there is a high chance that we'll cover the if you think of this as a state space, a space, you can cover all the corners of the space if you randomly generate those scenarios. So this was not possible until we had system Verilog. So after system Verilog, we got this support of randomized stimulus generation. We'll see this in more detail going forward, how we use randomized stimulus generation using constraints and randomization. Then the coverage. So like for the example of adder, there were 4 scenarios. We'll write 4 test cases, or even you write 1 test and you'll cover all the 4 scenarios. But what about designs which has billions of inputs, billions of combinations of inputs? So you cannot cover all of them. So there should be some metric which will tell you that okay, the verification is good enough. So with the current complexity in the design, verification is never 100%. So there's no design which will in the industry now, if it's a medium fairly complex design, no verification engineer will tell that this design is 100% verified. It's just some metric, will define some metric and will meet that metrics, and we'll say okay, this metric has been met. So that is what the coverage comes into picture. So for example, let's say there is a billion combinations of inputs. We'll select maybe 1 million or some thousands of those inputs, and we'll say that we'll cover this 10,000 scenarios, and then we'll say okay, the design is verified. So we still haven't verified the n minus 10,000, but when we verify 10,000, we are like more than enough confident that the chip will work when it is in the market, in the real scenario. So that is where the coverage comes into picture, and we do have classes and other support in the system Verilog to have that coverage metric in the test bench. So this was not there in Verilog, or for that matter VSTL. So then checking for the functional correctness. So system Verilog assertions and checkers, those supports again we have in system Verilog. So system Verilog is more about helping the verification engineer with the complexity of the design. So and then the reusability of the code. So like I was okay, so like I was saying earlier, since the designs are becoming complex and there's a time to market factor, so there's always a new chip coming. You know, the Qualcomm every 6 months launches a mobile chip, a mobile SoC Snapdragon. So you cannot wait and try to code every test, every new test bench for every other project, because if you end up using 6 months and 1 year for writing a test bench, then when will you verify the design? So that's not possible. In real scenario, you'll just get 2 months, 3 months to write your test bench. And it's always delta, it's always built on top of what already is there. So a new generation chips comes is built on a old generation chip. So if there's a Snapdragon 810, it will be built on some 750, 760 kind of generation. So when the companies do that, then there's a delta changes in the feature of the design. So similarly, we have a delta changes in the test bench based on what design have changed. So to use the old code in the test bench, we need a reusability of the code. So for that, we have different support in the system Verilog, like classes and objects, inheritance. So those concepts from C++ are ported into system Verilog. So, and helps us in the reusability and scalability of the code. Then there's again important factor like the consumption of memory. So Verilog is a static language, like whatever you define a wire or a variable or anything or a FSM, that consumes some memory in the system. And whenever a simulation runs, simulation asks for that memory from the so whenever you code any design or test bench in Verilog, that runs on a simulator, maybe a Synopsys or Cadence or Mentor graphics. So that simulator will run again on the CPU, right? And that CPU, so that simulator needs some memory from the CPU, because you are asking that memory from the simulator when you write that code in the Verilog or system or VSTL. So what if with the complexity of the design and the test bench, you have to write a lot of signals and variables, everything, and that will end up consuming huge memory. So that's not feasible with the complexity of the design nowadays we have. So we have like a dynamic memory management, like objects. So when you create a class and when you create an object of that class, so we allocate a memory to that, and that memory allocation is dynamic, like you allocate when it's used, and that memory is destroyed when the work of that object is completed. So it's dynamically requested and destroyed. So you don't need a memory from the start of the simulation to the end of the simulation. So you have to think on these angles also. Now being a verification engineer is not only about verifying the design. Your test bench needs to be fast, it needs to be very compatible, reusable, and it needs to be consume less energy, because you have like billions of scenarios to verify. And if you just end up wasting time and memory in your test bench running, then the verification is going to be slow, the simulation is going to be slow, and you will probably not close, because we just don't want 10,000 scenarios which we have defined in the coverage. We want to cover millions or maybe possible billions of scenarios. So yeah, those are the limitations, and those we have addressed in system Verilog. So yeah, system Verilog has adopted its features from OpenVera, E language, C++, System C. Different features are coming from different languages, the assertions or the coverage or the classes. So it's a unified design and verification language. So we call it HVDL, HDVL. So it's no longer a hardware description language. It's a hardware description and verification language used to design and also stimulate and verify the functionality of digital circuits at different levels of abstraction. So by abstraction, we mean like we have brought in concepts of classes and structs and inheritance. So we can build layers on layers and layers, and it will help us reduce the complexity and also build help us reuse the code into different projects and different IPs. So maybe some code we have built, like when a SoC is built, there are different components in SOC. Like there can be a GPU IP, there can be a processor, there can be audio IP. So if there is a level of abstraction and from the like if you have coded a scenario or a part of the test bench at the level of audio IP, that probably can be reused at this SOC level because the verification is now no longer limited at one level. The same feature is verified at different levels, like at the SOC level, at the subsystem level, and at the IP level, and at the sub IP level also. Now again, I'm just repeating it because of the complexity of the design. Now it's not sufficient to verify the feature at one level. We have to verify it at multiple levels to make sure that there's no bug escaped in the silicon. Because if bug escapes in the silicon, it's a very big cost to the company. Because sometimes you may have to redesign the chip or refabricate the chip, and which is called the respinning, and it costs a lot to the company. So yeah, and since we cannot cover all the scenarios, we just try to cover as much as possible at different levels of abstraction, different levels of verification. So basically, system Verilog is a superset of Verilog along with different other features brought from different other languages. So these are the major strengths of system Verilog. It has new data types, for example, logic. So logic is a very strong data type. I will discuss more about it. And logic has really made system Verilog very strong. And now we don't really have to care much about res or net, all that we used to do in Verilog. And then there's a constant randomization. So basically, by constant randomization, what it means is, so you randomize the inputs. Like if there's an adder, there's a and B, we'll randomize it. It can generate 0, 0, or it can generate 0, 1 or 1, 0, 1, 1. We don't know, but we'll just call a function randomize and it will generate one of the possible combinations. Okay. And by constraint, we means will within the specification of the design. So we'll write some specifications in the test bench. Like there will be a specification of the design. Based on that specification, we'll write some constraints in the test bench, and then we'll randomize. So basically, the inputs will generate within that constraints. So basically, within that specifications, because we do not want to verify a design which will never verify a test or the scenario in the design which will never occur in the real silicon. So to make sure that everything is verified within the real scenarios, we write constraints, which is based on the specification. So that is where the constraint randomization, and it's a very, very, very important feature. The constraint randomization is like a, what do I say, a boon for the verification engineers. Without the constraint randomization, it's very hard to imagine how programming support. So this coming from C++ and all other languages. So this helps us reuse the code and creates different levels of abstraction. So with the different levels of abstraction, what I mean is the complexities are hidden. Like for example, there's a protocol. Let's say the processor, some other IP is connected to the processor using let's say an AXI interface. So you don't have to if you are not verifying the AXI interface, you don't really care about the AXI interface. You just want to send some transaction to the CPU. So if you want to do that, you can just use, you can instantiate the objects of the classes which implement that protocol. And just you want to call some function and it will send some transaction to the CPU. You don't have to implement that all the time in your test bench. Every time you create a test bench around the AXI interface. So with that level of abstraction and reuse, you just instantiate it and you don't care what is happening inside. So OOP helps us with that. It provides an abstraction and reusability, and definitely help us with the scalability also, because there can be multiple interfaces of AXI. You just instantiate it multiple times. Then there's coverage. Coverage is a metric that is used everywhere, like every verification engineer use to say that their design is completely verified. Though no design is 100% if it's a complex design, it's never 100% verified. But by using coverage, we tell that it's 100% verified. Because coverage is basically a mutual agreement between a verification engineer and a design engineer, and maybe architects. They mutually agree, they sit together and mutually agree, okay, if we cover all these scenarios, like out of millions scenarios. By scenarios, I mean the combination of the inputs, including the FSM states. So if there are millions of combinations of inputs, we cannot test all of the inputs, right? All of the combinations. So if we say that if design engineer, verification engineer, and the architect, they all mutually agree that we'll cover these 10,000 scenarios, and if those 10,000 are tested, we'll say the design is fully verified. So that is where the coverage comes into picture. So this is basically a mutual agreement. Verification engineer will verify 10,000 scenarios. If that is verified, then if he does more than that, it's good. It's well and good. If he doesn't do more than that, it's still okay. Like we can say that it's fully verified. But there are chances, but it's a very low probability that some bugs will escape in the silicon. But that's a very low probability. So then there's a easy C model integration. Basically, you can integrate C model into your design, into your test bench. So, sorry. So if there's a complex IP and you want to create a checker around it, okay. So let's say you are verifying what should I say, a DDR. So a DDR file, let's say, connections from the memory controller to the DDR. So if you want to verify that connection, verify that IP, you want to create a golden model of it, okay. And like if you send something into the input and there's an output, how do you verify that the output is correct? You'll compare it with something, right? So that comparison, what will you compare it with? So basically you'll create a model, equivalent model of that IP, maybe in C, and then you'll give that input to their design, and also you'll give that input to their C model, and then you'll compare the output of the C model to the output of the design. So that is one of the use case of this C model integration. So basically you are creating a golden model, and then you're comparing the design output to the your golden model output. So you can integrate those output, or if those C model. But if you don't want to model that in the C, you can model it in your system Verilog or Verilog and any other languages. But modeling any design into a C language is very easy. So people usually model their design into C and then integrate into their test bench. So this is where the C model integration becomes very useful using. So this is done using direct programming interface feature in the system Verilog. Then assertion based verification. So assertion is basically nothing, like it's a checker, a different kind of checker, which tells that if some events happen at the input of the design or somewhere in the design, what should be the corresponding output and what point of time. Like in case of our adder, if there was A and B was both 1, then the outputs sum should be 0, 1, 0. So that we can write in assertion. If A is 1, B is 1, then we can say C is 1. So assertion will, every time keep checking whether this condition is true or not. If ever this condition is not true, it will flag an assertion. That is why we call it assertion based verification. So these are like a very I would say strengths of the system Verilog, which makes system Verilog very useful and widely used in the industry. It has replaced VSDL, it has replaced Verilog, and it's the most widely used language, both in design and the verification. So any question you have until here?
No, sir.
Okay. Sorry.
No, sir. It's clear.
Okay. So let me move forward then. So we have discussed these points. So it has a bit better memory management, and like it because of queues and objects. Then we require less RTL and test bench code because of reusability and other different features from the C++. There's a higher level of abstraction. Then by abstraction, I'm saying it again and again, it means because we are hiding the complexity in the lower level of the test bench, and we are just using a wrapper around that complexity. So, and then there are new data types like byte, short int, long int, wait, logic, string, C handle. So C handle is kind of a pointer. Yeah, like we use int star p. So those kinds of functionalities there in the system Verilog also. Then there's a type def, struct union, tagged union enum, and there's a dynamic and associative arrays, queues, classes. We can discuss this, some of them. We'll discuss some of them, and yeah, you can also go back and look into what all these are, and we can discuss this in future classes also. Okay, so to start with, today we'll cover only the data types, and then in the future classes, in the further classes, we'll discuss other features of the system Verilog. So to start with, what are the value sets in the system Verilog? So it has like original Verilog language had 4 state values, where each bit of a vector could be either 0, 1, G, or X. So 0, 1 is like 0 is the ground, 1 is the high voltage. And I guess you all guys know, being you having the background for the digital electronics. And G is that nothing is connected to it, it's high G. And then X is that it's in a metastable state. Maybe it's 0, maybe it's 1, we don't know. So X is a very important, when you look from the verification perspective, because sometimes in the design, because of metastability and because of the setup and hold issues, you don't know what the output is. So you need such kind of data types which can reflect the actual behavior, what is happening in the design. If there's a X, then if you see an X at the output, then that means there's something wrong happening. Something is wrong. There's maybe setup violation, hold violation, or metastability. We don't know, but there's something wrong. So then system Verilog added the capability of to represent 2 state values also, where each bit of a vector can only be 0 and 1. And we need this support also because it helps to speed up the simulation. Now, as you discussed in the beginning of this session, simulation time has become a very important factor now. You don't want because we have tests which runs for weeks, which for days. You cannot just run a test and then wait for 3 days and get the result. There are tests, such tests in the design in the industry now. We have to wait for 1 week, maybe 10 days, 3 days. There are tests like that, and you cannot waste so much time for running a single test, and you have to cover like millions of scenarios. So you need to speed up the simulation time, and for that, probably system Verilog has added the 2 state values. Then system Verilog also added the bit and logic keywords to the Verilog language to represent 2 state and 4 state. So bit is 2 state and logic is 4 state. So 2 state means bit. Whenever you declare a variable name starting with bit, so that can take only 0 or 1. It cannot take X or G. But if you declare anything with logic, it can take any of the 4 values. Then system Verilog net types such as wire only use the logic 4 state value set. Then the bit and logic keywords can be used without explicitly defining a net or a variable, in which case a net or variable is inferred from the context. So now you don't really have to care what to declare as a net, what to declare as a res or a variable. We just use it, and this system Verilog and the simulator itself will figure out. So it's very easy now because it was adding unnecessary complexity into our design and the test bench. And I think that's here. The system Verilog, the keyword bit always infers a variable, and the keyword logic infers a variable in most of the context, but also infers a net if used in conjunction with the module input and output. So in input and output, we usually use net or wire, right? So it will the logic will be inferred as such if it is used in the module definition. Otherwise, it's mostly the res. So there's an example here. So if the input is I1 in the module definition, it's basically a net with a 4 state value. If input logic we declare, then again it's a net with 4 state. But if you declare input bit I3, then it's a 2 state variable because bit is 2 state and logic is 4 state. And then if you declare output O1, then it's a net with 4 state set. And if you declare output bit O3, then it's again a 2 state variable because it's declared as bit. So most of the time, I hardly find people using bit other than test bench, because in design you have to use logic, because design you don't know whether it can be either 0, X, 1 or G. So mostly design uses logic, but in test bench, if test bench, we are not verifying the test bench, right? So we are verifying the design. So test bench, we can still use bit. and it doesn't matter because test bench doesn't care about X and G. Test bench do care about X and G, but in the design, not in the test bench itself. Then by using the explicit, like if you declare bit clock, it is a 2-state variable. If you declare a logic reset, it can be a 4-state variable. Then if you declare a logic array of data, then it's a 4-state variable data. Then if you declare a wire logic, then it's again a 4-state net. And similarly, a variable explicitly will be declared. It's inferred as a logic, which means it's a 4-state. So yeah, there's nothing much here. A simple correlation to the Verilog language. Then so system Verilog, the advantage of the system Verilog here is now you no longer need to worry about when to declare the modules as wires or arrays, or more specifically a net or a variable. You just declare them as logic, and the language and the simulator will take care of it. So it removes the unnecessary complexity from the designer and the verification engineers. Sorry. So in a test bench, randomly generated test values should be declared as bit rather than logic 4-state. Yeah, most of the time we do follow it, like we declare as bit because we don't usually give X or G as the input to the design. So we usually declare the variable as bit, but at the output we need logic, because at the output of the design, the test when we sample the output of the design in the test bench, so we can the design can give us any of the 4-state values. So there at that point, at that place in the test bench, we need logic, because we want to sample X also. If the design is giving X, we want to know it, because if design is giving X, then there is something probably wrong and we want to know it. So we cannot use bit there, but at the input side, we usually we never give X to the design. So in that cases, we use bits at the test bench when driving the inputs, and when sampling the outputs, we use logics. In some corner cases, we do use logic at the inputs also. When we are not verifying the design and we want to, like some of the signals are don't care, right? Like you may have seen in your digital electronics, some of the variables are don't care. So in those cases, we do supply X in the inputs of the design also. So if we do that, then there also we define as logic. So it's basically like a way to use bit and logic. Bit is the only thing to remember here is bit is 2-bit and 2-state, and logic is 4-state. So wherever you want to use 4-state, define it as logic. Wherever you want to use as 2-state, define it as bit. Nothing else we need to care about when we are using system Verilog. No need to care about net, wire, or res, anything like that. Okay. So nets type, what is net basically? Net is basically a synthesizable net types. So it can be declared as wire and try. And so this is basically used for interconnection between the modules, and it also support and allow multiple drivers. So they can be multiple drivers, they can be weak. So you can probably go back and study about it. So it can be weak 0, weak 1, strong 0, strong 1. So if there are 2 drivers to a net, if someone is driving weak 0, and other is driving strong 1, then the strong one will take will be dominating the weak 0, and that net will be driven as strong as a 1. So yeah, so these are the basic concepts coming from Verilog itself, and it's hardly used in like we do use wire, but try and all is hardly used in test bench or the design. And supply 0, supply 1 is basically the supply that we like to mimic the supply of the power supply. So some of the gates, like we needs one ground and the high VDD connected, right? So for that we use supply 0, supply 1. So supply 0 is always grounded, so it's always assigned 0, and supply 1 is always connected to the VDD, so it's always assigned 1. Again, to mimic the real digital electronics, like at the gate level. Then we have other net types like WAND and try and war or try-or. So basically, it will AND different wires or do an OR of different wires. Like at the we don't need gates, so it's basically at the wire level we'll do an OR or AND of the multiple drivers and give the final output to the net based on what the variable, what type we have used whether it's AND. So if it's like W AND WAN, then we'll use an AND of all the drivers and they drive the final output to the net, to the wire. So WAN can be considered as like an AND gate. So depending upon what is driven at the inputs, will drive at the output. Okay, and then on the variable types. So variable types are mostly used in procedural code. We'll see what procedural code is, and so there can be always an initial blocks, and inside always an initial blocks we use different variables. So those are used. Anyone asking any question? Okay, I guess so. Can you mute yourself? Yeah, okay, now it's gone. So yeah, so basically the variable types. So as we know, like we want to reduce the complexity, right? So we use different kinds of procedural statements to reduce the complexity in our design as well as verification. And so for that, there's an example like always block or initial block, and always block can be used to mimic a combinational logic or a FSM. So for both we can use always block. And so in always block we use variables. So we'll see how that is used when we look into the procedural code. And then Verilog and system Verilog requires like the left hand side of the process assignments must be a variable type. So whenever you use always blocks, we have to use a variable, a logic type, or we cannot use wire inside always block.